All right, hello physicists. Today we're going to kind of barrel through a lot of stuff. My goal for today is to try to set you up so that over the weekend you'll be able to do a lot of your homework problems and also to get most of the ideas, almost all of the ideas on the table that are going to be relevant for the test next Friday. So we're going to be first reviewing our applications of Gauss's law. On Wednesday, our video was about Gauss's law, and we discussed some applications, but we're going to make sure that you're set up to do your homework on that. And then we're going to introduce two ideas that are very important for the rest of this course. The idea of the potential energy of different charges and of the electrical potential. And the electric potential is especially important because in the lab, we don't really measure electric fields very often. Most of the time, we measure electric potential. So if you ever measure something in volts, that is a potential difference measurement. Okay, so we're going to try by the end of today to do a couple quick examples so that you understand what we mean by electrical potential energy. How to find the electrical potential energy between two point charges and between groups of point charges, and we're going to try to calculate E from the V. So the potential includes for static charges the information that we need to get our electric field. And then this last one is the only one that we're going to leave for Monday. Okay, just as a quick reminder, I have put up a reflection question. It wants you to answer what is electric flux. Remember, electric flux has to do with the area of a surface and the electric field going through that surface and the relative angle between them. So it depends on all of those things. And then I also ask you, how is it possible for Gauss's law, given Gauss's law, for the electric flux of a small sphere containing a point charge to be the same as the electric flux of a large sphere containing the same point charge? And that just has to do with the electric field being smaller for the bigger surface. The electric field is smaller if we're farther out from the charge. So the flux, the electric field is smaller. The flux is the same though, because the electric field and the area trade off. When the electric field is big, the area is smaller. When the electric field is small, the area is bigger. So those two things cancel out exactly to give us Gauss's law. And the other thing I want to remind you of, so these are the two things that are due on Monday, is you have to just write a couple sentences about Gauss's law, and you have to take your quiz. So this is a 10-question multiple choice quiz. And that's all I'm going to say about that. All right, so remember from Wednesday, Gauss's law has to do with adding up the flux through a closed surface. And if I have field lines that go in and come back out, they're going to give me a total flux of 0, because over here the area vector is going to be pointing opposite the direction of the electric field vector. We would get a flux contribution that's negative. On the other end, over here we would get a flux contribution that's positive, so those would cancel out. The only time we get flux contributions that are non-zero is when the charge is inside of the surface. So our Gauss's law says that if we add up the total flux coming out of a surface, that will tell us about the total charge in that surface. Now, the reason that we were interested in that is that sometimes this can be a huge simplifying device for finding the electric field for different distributions of charge. So here's a nice example. This is an actual homework problem I've given you. It says in figure 2323, we see a metal ball, two spherical metal, so here's your metal ball, and two spherical metal shells. So these gray things are the shells. And then they are asking us, that they tell us we want to find the electric field on these three surfaces. So we're finding the magnitude of the electric field. Everything is spherically symmetric, so the electric field should be pointing out or in. In this case, let's see how this works. They say that down here, in our little charge, we've got Q spread out over the ball. For our smaller shell, we've got 3Q spread out over that gray shell. And then for the largest shell, we have 5Q spread out over that shell. So remember, Gauss's law tells us that the total flux, and keep in mind the flux is our electric field times our area times the cosine of the angle between those two. But for this example, at every point on our Gaussian surfaces, our electric field and our area elements are pointed in the same direction, so the angle between those is going to just be 0, and the cosine of 0 is 1. Okay, so in this case, it's going to be 1 for all of our things. And it wants us to rank what is the size of the electric field out here versus the electric field in here versus the electric field on there. Okay, so I'm going to do 2 of these with you, and you can do the middle one and finish this problem up. For A, if we want to find the smallest, okay, we should have that epsilon naught times the electric field times 4 pi r squared, and let's call this our 1, 2, and 3. Or so here's my smallest would be my first surface, and my r here is the radius of that first surface. Let's call this our E1 is our electric field at that surface 1. Now Gauss's law tells me that this is related to the charge that's enclosed. So my Q here is in the middle of that, and that's all the charge that's enclosed. This 3Q and the 5Q are outside, so they don't contribute. All right, so I can now go ahead and find what E1 is. E1 equals Q over 4 pi epsilon naught r squared. Okay, now let's see how that's different for my largest. Whoops, so I'm gonna let you do 2. I'm gonna show you 3, the largest one of these Gaussian surfaces. We're going to find out what's the magnitude of the electric field out here. Well, according to this Gauss's law, I've got my epsilon naught times, let's call that E3. And then I have 4 pi r squared, but in this case, the r is going to be 3 times the r of the smallest one. So let's put in 3r squared equals, okay, now I have to add up all the enclosed charge. So in this case, I have Q plus 3Q, that gives me 4Q, plus 5Q. So the total amount of charge that's enclosed in here is 9 times the amount of charge that was enclosed in that first circle. So it would be 9Q. So that's just me applying Gauss's law as before. And let's see what we find. So E3 equals 9Q divided by all of this stuff. So I'm going to have 3 squared r squared. So that's going to give me, let's just keep this the same, 4 pi epsilon naught, 4 pi epsilon naught, and my 3 squared is going to give me 9, and my r squared, we'll just leave that as r squared. Now notice what happens. This 9 and that 9 cancel, not because of any, not because they would need to cancel, but just in this specific case they do, such that E3 is the same magnitude as E1. Okay, so if you're ranking the Gaussian surfaces according to the magnitude of the electric field, the magnitude is the same for that small surface and this large one. It wouldn't have to be that way, but in this particular example, they've kind of put their thumb on the scale to make sure it turns out nice. So I'm going to let you figure out what the magnitude is for this middle one, and then rank them according to how big they are. Here's a little bit more of a sneaky example. They say that you've got a drum of a photocopy machine. That's like this roller. Has a length of 42 centimeters. So let's say this L equals 0.42 meters. And a diameter of 12 centimeters. So that D equals 0.12 meters. It asks the electric field just above the drum surface is 2.3 times 10 to the 5th newtons per coulomb. Okay, so we're assuming that this electric field is kind of going to be pointing out radially. 2.3 times 10 to the 5th newtons per coulomb. Okay, and then it asks, what is the total charge on the drum? Now, if we're assuming that all of this electric charge is on the surface here, and our electric field is going to be pointing out radially like this, we can use our Gauss's law to find that E. How do we do it? Or rather, to find Q in this case. How do we do it? Well, for part A, we're going to go ahead and say epsilon naught times the surface area times the electric field equals that Q enclosed. And that's what I want to find. So all I have to do here, I'm given E. My surface area is just going to be the circumference of the drum times its length. So that's a length times width type of surface area. So it would be, in this case, epsilon naught times L times pi d times E equals my Q enclosed. Okay, so that's just putting in the factors. Now, the part B asks something different. It says, the manufacturer wishes to produce a desktop version of the machine. This requires reducing the drum length to 28 centimeters. So L in this case is going to be 0.28 meters. And the diameter to 8 centimeters. Okay? Diameter to 8 centimeters. 0.08 meters. The electric field at the drum surface must not change. So it's still going to be this number. And then they ask, what is Q enclosed in this case? Well, you're going to do exactly the same thing, except you have a different L now, a different D, and same E. And so you're going to have a different Q enclosed. All right, so this is the sort of problem that you can do with Gauss's law. It's a little bit sneaky because it's forcing you to make some assumptions about the symmetry of the field, and that you're not including the caps because the charge is going to be all on the outside and the electric field is going to be 0 inside of the drum. So just to dilate on that point a little bit, if you have a conductor, electric charge always arranges itself on the outside of that conductor such that the field is 0 inside. And this is not really a statement so much about the conductor, so much that it is that when we define a conductor, it means that the charges can move around pretty freely in there. If the electric field is not zero, they will continue to be accelerated within the center of the thing. And in fact, they'll continue to be accelerated until they've all moved around. And once they stop moving, that basically tells you that the electric field is zero. So it's not that deep of a result, but it is a little bit of a conceptually important one, which is that electrostatics requires this E to be zero inside of the electric inside of the conductor. Otherwise, we would call it something else. It wouldn't be a nice conductor. Now, this also has an interesting result, which is that, let's say that you put a conductor inside of a ring of another, or a charge rather, inside of a conductor. Well, what happens here is that the total electric charge inside the conductor is zero. And so you notice that if you put this minus charge, for instance, not at the center of the conductor, the plus charges on the inner surface of this spherical shell are not going to be radially symmetric. They're going to have to collect more strongly on one side of the ring than the other. And that's to cancel out the electric field inside of this. However, because some of the electrons had to be repelled to the outer surface in order that you have that positive charge to cancel out the field of the negative charge that's inside, you still are going to have that extra negative charge on the outside, but in this case, you're going to still have a spherically symmetric field outside, and it's going to be centered on the center of the conductor rather than on the center of the minus charge that's in there. So this is an interesting application, because if you've ever watched any conspiracy shows, you'll see that the trope of people putting a tinfoil hat on themselves. This has to do with that. It has to do with, if you want to keep electromagnetic signals from getting in, you can put this type of a cage called a Faraday cage around you, and this is a nice demo at a museum, and it can shield most of the electric signal from getting in. Okay, so in our last video, we also talked about two nice applications of Gauss's law. One was that we could solve for the electric field of a line of charge. The other is that we could find the electric field of a sheet of charge. And just to remind you how this worked, we can quickly do the sheet of charge again. In this case, if you have this infinite sheet of charge, the symmetry of the problem requires that the electric, if this is a positive sheet, for instance, that the symmetry of the problem requires that the electric field is pointing radially out from the sheet. And from this, the sheet, you're going to have, we can use any kind of Gaussian little pillbox that we want. Here we can use, for instance, a right cylinder. And the sides of the cylinder will not contribute to the flux, because the area elements coming out of that will be perpendicular to the electric field. So when you calculate the flux, remember the flux has to do with the E times the little area elements times the cosine of the angle between them. So you'd have to take all little pieces, but the area elements on the side are always going to be perpendicular to the electric field, so the total flux through the sides is going to be zero. On the other hand, here you have some flux on the left side and some flux on the right side. And the total flux is going to be the sum of those two. And it's going to be equal to the electric field over here times the area plus the electric field over there times the area. Now I'm being a little glib because I'm noticing from the symmetry of this problem that there's no reason for me to expect if I have this Gaussian pillbox equally spaced on both sides, there's no reason for me to expect the electric field to be different on either side. So I'm saying the electric field on the left is the same as the electric field on the right. The area on the left and right is the same because of the way that I've constructed this Gaussian surface. So the total flux would then just be 2 times the electric field times that area. Now, if you want to look at the amount of charge in here, the way that we've put our charges in terms of this sigma, and sigma has units of coulombs per meter squared, and if we want to find how much charge we have, then we just have to take times the meter squared, times the area. So our Q here would just be sigma times whatever area is in that little part of the sheet. And so now we can go ahead and use our Gauss's law. Gauss's law says that our epsilon naught times our flux gives us the Q enclosed. So our Q enclosed is our sigma times A. So epsilon naught times 2 times E times A is equal to sigma times A. And just as we found with the line of charge, we had the length of the line of charge cancel out. Here we're going to have the areas cancel out. And our sigma is equal to, we want to find our electric field magnitude. Our electric field magnitude is equal to sigma over 2 epsilon naught. And remember, epsilon naught is just a constant, a measured constant that's related to Coulomb's law. Okay, so that's the same as this result. Now, in your homework, I'm asking you to apply these results. Now notice that this one depends, for the line of charge, the field does get smaller as you go farther away. It dies off as 1 over r. That's as opposed to the dipole, which dies off as 1 over r cubed, and the point charge, which dies off as 1 over r squared. On the other hand, the sheet of charge, in this case, we're imagining an infinite sheet of charge. The electric field does not die off in space. So it's a little bit of an interesting case. This is a good approximation if you have a charge that's close to a charged sheet or a charged region of a piece of metal or something that's much larger than itself. Okay, so if you have like a little atom on top of a sheet, this is a pretty good approximation because you can calculate what the charge per unit area on that sheet will be. Okay, so let's do a little bit of a practice on this. It says, look at this situation. We have 4 very long rods extending into and out of the page. So that our case here, imagine that we have like transmission lines or something like this that have charge on them. And we're given the charge per unit length in terms of microcoulombs per meter. Okay, so they give us this +3, for instance, means +3 microcoulombs per meter. So it's a charge per unit length. That's the right units for this formula. And it says the rods are separated by d or 2d as drawn. So this would be a distance of d, for instance. That would be a distance of 2d. And a central point is shown midway between the rods. Okay, that's this. Rank the situations according to the magnitude of the net electric field at the central point greatest first. Okay, so let me show you how to do this problem. I'm giving myself a little bit more space here. Let's look at just A. Okay, so this is, I'm going to have +3 plus 2. There's my x. This is the point where I want to find the electric field. Minus 2, minus 3. Okay, so this is telling me the lambda, the charge per unit length. Notice that my electric field is proportional to lambda over r. Everything else is just going to be a constant out front. So if I want to, in this problem, I can kind of forget about all those other constants and just worry about lambda over r. Now, since this is an electric field problem, I do have to worry about vectors. So the electric field points out from positive lines of charge, it points in towards negative. So here I'm going to have 4 different contributions. Here's a plus. I'm going to have my E from my plus 3 pointing towards the plus x direction. Plus 2, E points away. And then I have my electric field pointing toward my negatives, so I'm also going to have the E from my minus 2 is pointing towards this one. The E from my minus 3 microcoulombs per meter is also going to be pointing to the right. So in this case, my E is going to be proportional to 3 over R. So in this case, it would be 2D plus 2 over just D. How am I finding that distance? It's the distance to this point where we're finding the electric field. These are all going to add together as vectors. Plus, here's my E from my minus 2, would be 2 over D. Now, why am I having a positive 2 here? It's because the electric field, I have to put in by hand the direction. The direction has to do with whether it's going to be pointing towards or away. And I drew in this picture first. So I know this is pointing in the plus x direction. So be careful. Don't just mindlessly put in the minus on top here. And then for my minus 3, it's going to be plus 3 over 2D. Okay, so I can add these together. You know, this 2 over 2D. I'm making a 2 over 2D. So this is going to be proportional to 3 plus 4 plus 4 plus 3. So that's 6 plus 8 is going to be 14 over 4D, or sorry, over 2D. So proportional to 7 over D. Okay, on the other hand, for part B, you can notice that just as before, if you have a line of charge that's equally spaced from your point, you do have the same kind of cancellation because this one will provide a electric field component to the right. This one will provide an electric field component to the left. Those cancel. These cancel. Here your electric field contribution is just 0. Okay, and then maybe I'll leave the rest. Well, let me do one more just to make sure that we're seeing how you would do this. Let's do yeah. This one you can see is also going to be 0 because of the contribution, and then so you know that B and D are going to be the smallest. Really, all you have to do is compare A and C, and then so this. The only difference here is that the distance to this far out one is going to be 3D because this is D, 2D, 3D, D, 2D, 3D. Okay, so I'll let you finish that one. If you have problems on it, let me know and we can finish it on Monday. Okay, here's another example where you have to worry about the direction of the electric field when you add up the contributions from multiple sheets of charge. So if you just had one sheet of charge, you could just use this equation, plug in this, and this has to have units of, to get an E that's in units of newtons per coulomb, you have to put in a sigma that's in units of coulombs per meters squared, and then epsilon naught is just the number. Maybe I should put that down here. Okay, yeah, so just to give it to you on this video, epsilon naught is your 8.854 times 10 to the minus 12 coulombs squared over Newton meters squared. Okay, so you can check for yourself that the units work out on this. So they give us these charge densities in terms of microcoulombs per meter. So that means you have to take this times 10 to the minus 6. So charge density 1 is going to be plus 2 times 10 to the minus 6 coulombs per meter. The second one is going to be plus 4 times 10 to the minus 6 coulombs per meter. Sorry, coulombs per meter squared. And charge 3 is going to be minus 5 times 10 to the minus 6 coulombs per meter squared. Now, notice that there's a tricky, a little bit of flarf in this problem. Flarf is the term I use for unnecessary information. They give you these distances to point P, but this E does not depend on distance. It just depends on the sign. So since this at point P, we just have to think, is my electric field contribution going to be pointing towards the sheet or away from the sheet? So we're going to have an electric field contribution from 3. We're going to have an electric field contribution from 2. We're going to have an electric field contribution from 1. How do I find the magnitude of that? Well, I just plug in this number divided by 2 epsilon naught. Okay, so I'm going to find a magnitude for 3. I'm going to find a magnitude for 2. I'm going to find a magnitude for 1. And now, at point P, I have to determine by hand whether it's going to be the electric field magnitude is going to be pointing towards or away. Okay, now E3 from this charge sheet 3 this is a negative charge, so we're going to be pointing towards. So there's my E3. My E2 is positive charge, so it's going to be pointing, my electric field contribution is going to be pointing away. So there's my E2. And the E1 is also from a positive charge, so it's going to be pointing away. Okay, so when you find your total, it's going to be E1 plus E2 minus E3. Okay, so you're going to calculate your electric field magnitude for each one of these. We determine what direction our electric field contribution is going to be at each one of those points, and then we add them together, and that gives us our total electric field. Okay, so give those a shot. Notice that now we have a couple of different charge distributions, and these are the 4 that I want you to be comfortable with for your test. A point charge, 1 over r squared. Your dipole, remember this is it depends on the P, which is your Q times D. It's a plus and a minus charge. that are separated by some distance d, so that's what this Q is. It has units of coulombs times meters. Then we have a 1 over r type of charge from the line of charge. That has the sigma has units of coulombs per meter. And then we have one that's due to the sheet of charge, and that should have coulombs per meter squared. And that one does not die off in space. So 4 different examples that you should be thinking about, getting comfortable with, because they will all show up on your test next week. All right, now our last ideas of this unit. We're going to try today to introduce the ideas of electrical potential energy and electrical potential. And electrical potential is something we're going to use a lot. Voltage. In this unit, we're going to be measuring voltage with a voltmeter a lot of times. So this is going to be the beginning of a long romance. So here's what I would like us to think about first. Let's say that we have two particles, and let's have them have charges Q1 and Q2. All right? Now, the force on Q2 is going to be pushing in the plus x direction, because let's assume for the moment that these two are both positively charged. Now, if these are infinitely far apart, we know from our dipole example of last week that where we choose to be the zero potential energy is sort of arbitrary. So in this story, we just want to consider our zero potential energy as when these two particles are infinitely far spread apart. Now, if we want to calculate the amount of potential energy that the system has, we're going to calculate the amount of work it takes to push them together. Okay, so if we put in that work, we can get that work back out when they repel one another. And so if we want to calculate that, it's going to be minus the work, or minus the force times the distance. And we're going to integrate that from when, so this is our Q1, let's put at x equals 0. This is at our x equals r. And we're going to start that out from an r of infinity. So this is infinitely far away at the beginning, and we're pushing it toward our Q1. Okay, and it's going to end at that distance r. Okay, so if we put in how big that force should be, it should be a size of infinity to r of 1 over 4 pi epsilon naught. The force is going to be Q1, Q2 over x squared. This is just our Coulomb's law, but our distance, we're just considering it along our x direction. And we're going to integrate that over the distance that we're going to be pushing this. So we're pushing this particle in towards the other. And that integral is easy enough to do. The integral of 1 over x squared, or x to the minus 2, is minus x to the minus 1. So this would give me minus Q1, Q2 over 4 pi epsilon naught. And then this would be just minus 1 over x. Okay, if you take the integral of the derivative of minus 1 over x, it'll give you x squared. So notice we had our minus out here at the beginning, then we're going to have our minus here, and then we're going to integrate from 0, x equals infinity to x equals r. And this one turns out not to contribute because 1 over infinity is essentially 0. X equals r gives us this one, and this is minus, and that is also minus, so minus times minus gives us plus, and here is our potential energy for a two-particle system. Now, let's say that we have a collection of particles that is many particles. Okay, so if we're going to look at a collection of particles, we can extend this idea. So let's say that we have 3 particles. So in this example from your book, we're going to use this idea of the 2-particle system and add up the charge, the energy between these 2 particles, the energy between these 2 particles, and the energy between those 2 particles. So if we have 3 particles, we have 3 pairs. So let's see how this works. So our Q1, they tell us, has a charge of plus Q, and they tell us, assume that this is in nanocoulombs, so that's 10 to the minus 9th coulomb, or 10 to the minus 9th coulombs. Our Q2, they say, let's assume that that has minus 4Q, and our Q3 has a plus 2Q. Now, something to notice about this formula for the electric potential energy between 2 particles is that the signs matter. If I have a plus and a plus or a minus and a minus, I get a positive potential energy. What that means is I would need energy to push them together. On the from if they start out infinitely far apart. On the other hand, if I have a plus and a minus particle, the plus and minus particle have opposite signs, so that means I would need to put in energy to the system to pull them apart. So that negative potential energy means that those particles already want to be together. They're pulling each other together, and I would need to put in energy to take them apart. So how do I find out the total energy? Well, if this is your particle 1, your particle 2, and your particle 3, you add up the energy from 1 and 2, so the U from 1 and 2, you add up the energy between 1 and 3, and then you add up the energy between 2 and 3. So you're taking all of the different pairs. So that's a little tricky to think about when you're having more than 3 particles, but we'll go through an example with that in a second. So what do you do then? You have 1 over 4 pi r times the Q1 times Q2. So in this case, for the U12, that would be Q times a minus 4Q, all over the D. So this is not R squared, notice. This is just how far these 2 are apart. Okay, then you do the same thing for U13, the Q1, 2Q. So this U12, because this is a plus and a minus, this will give us a negative energy contribution. This will give us a positive energy contribution because these are both positive. And then between our 2 and 3, we have a negative and a positive, so this will be a negative energy contribution. So then you can go ahead and they all have a common denominator. You can add up minus 4Q squared plus 2Q squared minus 8Q squared, and you'll end up with minus 10Q squared. And then at that point, your 1 over 4 pi epsilon naught gives you that 8.99 times 10 to the 9th. Your 10, and then your Q is what they give you here, 150 nanocoulombs, so 150 times 10 to the minus 9th coulombs. And there's a squared on there, so you have to square it. And then the D, they give you in 12 centimeters, but you have to put it in meters. And so you can go ahead and find an energy, and remember, energy is in joules. So that's the example they give in your book. Let's take a look quickly at the homework example that I gave you here. It says, how much work is required to set up the arrangement if Q is 2.30 picocoulombs? So Q is 2.30 times 10 to the minus 12 coulombs. A is 64 centimeters, so A is going to be 0.64 meters. And the particles are initially infinitely far apart and at rest. So we have 1, 2, 3, 4 particles. So if we want to add up our energy here, it's going to be all of the pairs. Okay, so we're going to have between 1 and 2, 1 and 3, 1 and 4, and then 2 and 3, 2 and 4, and then we're going to have 3 and 4. Okay, so that gives me all of my pairs. Now, just to see how these are not all going to be the same, if I have my U12, for instance, I would need to put in my minus 1 over 4 pi epsilon naught. Okay, so we know all those numbers. I would have a plus q and a minus q. So this would be minus q times plus q would be minus q squared over this distance, a. And you have to be careful because you're going to want to square that because we've been squaring all of our r's, but remember, we have not squared because we integrated. Okay, so that's easy enough. You get a negative energy because this is a plus and that's a minus. On the other hand, notice we have to use a little bit of care because the distance between my two particles is going to not be the same for all of these. So this would be, for instance, a times the square root of 2. So my U14, for instance, would be 1. So this U12 is going to be overall minus. U14, those two have the same sign, so it's going to be a plus 4 pi epsilon naught. And these both have charge q, so q1, q2 would again give me q squared. And then I would have to take it over the distance, so that would be over a square root of 2. Okay, so you have 6 different things to calculate: U12, U13, U14, U23, U24, and then U34, where we are, for our Q1 and Q2, going to be putting in the charge of 2, the charge of 4, the distance between 2 and 4, you know, if you were finding U24, for instance. Okay, now let's introduce our last idea here. We already have the idea of an electric field. And the electric field is sort of abstract because it's in newtons per coulomb. And that electric field could just be hanging out in space, and it only applies a charge or a force if we put a charge inside of it. So that charge has units of coulomb. If you put the charge inside the electric field, coulombs times newtons per coulomb gives you a force that's in newtons. Now we'd like to introduce the idea of an electrical potential. And just like our electrical field, the electrical potential tells us about what would happen if we were going to put a charge there. Now this is a little different though, because we've talked about electrical potential energy. Energy is in joules. Charge is still in coulombs, and the volts gives us how much energy, how much the electrical potential energy would increase if a charge were present. So that's going to be, our voltage is in joules per coulomb. So energy per unit charge that we put at a position. So just like the electric field, the electrical potential is something that's hanging out in space. I think that's okay to say. And in the case for static charges, or slowly moving. It's something that has a value at every point in space, and as it turns out, we're going to be able to get our electric field back from our electrical potential. Of course, volts is named after another dead guy, the Italian Alessandro Volta, who invented, you can see here, the early form of the battery, the voltaic pile. Now, as we've said before, you can't really measure an energy, but you can measure a change in energy. So that's what we're always going to be doing. We're always going to be looking at differences in voltage causing differences in energy. So if you have a Q that is moving from one position to another through a change in voltage, effectively it's having a force being put on it, and that changes the energy. So the Q times the change in the electrical potential gives you how much that particle has changed in energy. Now, remember, we have changes in energy if we have work being done on a particle. And essentially, the way that you get that electric force is from an electric field, right? So it turns out we can relate our electrical potential to our electrical field. And the way you go from an electrical potential to an electrical field is by taking a derivative. So the x component of the electric field is the derivative of the electric potential in the x direction. The y component of your electrical field gives you the minus the derivative of your electrical potential in the y direction. And the z component of your electric field is the derivative of your electric potential, how it's changing in the z direction with a minus sign. Now I know that's a lot to throw at you, but I'm going to show you two examples using your homework right now, and then we're going to go back and do more sort of conceptual frameworking on Monday. So here's a easy example with how electric potential energy can be gotten from changes in potential. So it says, suppose that a lightning flash and the potential difference between the ground and a cloud is 1.0 times 10 to the 9th volts. Okay, so that potential difference that they give us is 1.0 times 10 to the 9th volts. And volts is joules per coulomb. Then it says the amount of charge that's transferred is 30 coulombs. Then it asks, what is the change in energy of that transferred charge? Well, if you want to find the change in energy, you just have to take the charge times the change in the electrical potential. So you just need to take Q, 30 coulombs, times delta V, 1.0 times 10 to the 9th joules per coulomb. So big potential energy that you're going to get. Now B asks, if all that energy released could be used to accelerate a 1,000 kilogram car from rest, what would be its final speed? Well, you'll remember that here we could use our kinetic energy and say, what if you dumped all that energy into kinetic energy? So you could take that and set it equal to the kinetic energy. They give you the mass that they want you to think about, the 1,000 kilogram car, and find the V. Okay, so in the first part, you're going to be finding the U. That's part A. In the second part, you're going to be finding the V, the final speed of a car, if you were going to give it all of that energy. Okay, so we're linking a lot of things together. We're linking electrical potential energy, and then finally kinetic energy from last semester. Okay, here's another just quick example. I know everybody's okay at doing derivatives. It says the electric field potential at points in an XY plane is given by this. Okay, so what is that really saying? It's saying that it's getting bigger with X and it's getting smaller with Y. And it asks, in unit vector rotation, what is the electric field at the point? This. Well, if we want to find the electric field of the x component of the electric field, we would take the derivative with respect to x and take a minus on it. So minus dv dx, this is just a constant. This, the derivative of that is going to be 2 times x. So 2 times 2 volts per meter squared times x. And then the second part is not changing in x, so its derivative with respect to x would be 0. Okay, so there's our ex. Our ey would be minus a, let's see, how does this change with respect to y? Well, it's not changing with respect to y, it's changing with respect to x. So the derivative of this first term with respect to y is 0. The derivative of the second term with respect to y is going to give us a 2y, and we have a minus out front, so it's going to be plus 2 times 3 volts per meter squared y. Okay, and our Ez, well, this is not varying with respect to z. That is not varying with respect to z. So this is just going to be 0 newtons per coulomb. Okay, so now I can go ahead and put in my x and my y. Here's my x. There's my y. And you're going to get then an electric field component in the x direction, electric field component in the y direction, and an electric field component in the z direction. And you can write that as your E equals some I component plus, so your EX times I plus your EY times J, no K component, all units of newtons per coulomb. Okay, so I know that's a lot to throw at you, but my goal here is to give you enough information that you can get a lot done on your homework even before next week, because homework is due next Wednesday. I want you to try to make a good run at getting as much of that done this weekend as you can. So what have we learned? Electrical potential energy U in a system of electrical charges is defined with respect to U equals 0 when all of the charges are spread apart. We can find an electrical potential, not electrical potential energy, which is V, that tells us how much electrical potential energy would be changed if we introduced a new charge Q at some point in space which has an electrical potential V. Now that electrical potential V then can give us information about our electric field if we take derivatives of it in various directions. Okay, so I realize that's a lot. We're going to need to practice that more. But I think that's enough to get us going, and give your homework a try. You've got a discussion question to finish. You've got a quiz to take. Okay, so good luck, and thanks for watching.